Morning everyone, my name is Lucy Wilson. I'm a GIS consultant with the environmental consultancy ADAS. This was a piece of research work we did recently for a large utility company who have their infrastructure covers a large part of the country. And what they wanted was a tool to help them to identify site level pluvial flood risk for their infrastructure. So I'm sure all of you already know what pluvial flooding is, but just in case, pluvial flooding results from high intensity rainfall leading to overland flow and ponding. This is distinct from river flooding because this kind of flooding occurs without any influence from rivers or streams. Pluvial flooding can also occur due to exceedance of storm drainage systems. This can happen if the design capacity of the storm drainage isn't sufficient for the rainfall, or if there are blockages in the storm drainage systems. So the things that increase the risk of pluvial flooding are, first of all, the topography, that is the lie of the land. In particular, sinks or depressions in the ground where water can collect. Flat areas in the surface of the land which allows water to pond and doesn't let it run away easily. And also channels in the surface of the land which can direct flow towards certain areas. Another important risk factor is the presence of impermeable surfaces. And this is one of the reasons why pluvial flooding is such a problem in urban areas, because obviously the water can't be soaked away into the surface if it's impermeable. So this can either lead to collection of water on the surface or runoff. A poor drainage capacity within the catchment can also increase the risk of pluvial flooding. And this could be, for example, if a storm drainage system isn't suitably large enough to allow for heavy rainfall events. Urban structures such as buildings and roads can also influence flow. Roads, etc. can channel flow towards particular sites, and buildings and other structures can route flow. So the problem for this utility company was that during heavy rainfall in summer 2007, it became apparent that some of their sites that were outside of the Environment Agency indicative flood risk area were being affected by pluvial flooding. And in some cases this was leading to equipment loss and shutdown of these sites. They therefore decided that they would benefit from a cost-effective way of identifying high-risk sites, which would enable them to mitigate against flood risk at these sites to make them more resilient in future events. So the overall objective then of the project was to develop a low-cost screening level methodology suitable for identifying sites at highest risk from pluvial flooding. And I've highlighted low cost here because the infrastructure of the utility company covered such a large area. They wanted to keep the costs at a minimum. We divided the project into 4 phases. The first of these being an analysis of the topography of the land using a digital terrain model using GIS techniques. In the second phase we used simple rainfall runoff modelling to obtain an estimate of the peak flow of rainfall reaching these sites. In phase 3 we visited a few sites to ground truth the results that we'd had from phase 1 and 2, and also used the information gathered during the site visits to refine the method in phase 4. So phase 1 then was the topographic analysis, and for this we used an Ordnance Survey 10-metre digital terrain model, which is essentially a model of the bare earth which has an elevation for each of the 10-metre grid pixels. And this doesn't model man-made structures on the surface, so it's completely bare earth topography. We based our topographical analysis on published research, in which we used 3 criteria to assign a risk score for each site. And these three criteria were that the site coordinate was within 40 metres of either a sink, that is a depression in the ground, a stream channel or a flat area. And to do this we used ArcInfo GIS tools. So the first thing we had to do was to find the sinks in the digital terrain model. And for this we used a tool called a flow direction, which essentially assigns a compass point to each grid cell in the output grid from the elevation, which is defined by the direction of steepest descent from each cell. And the way a sink is defined is that if all its neighbours are higher, then it's defined as a sink. It doesn't have to be just one cell that's a sink, it can be a cluster of cells if all of its neighbours are higher, and therefore contributing flow towards that cell or cluster of cells. To find streams, we used another GIS tool called flow accumulation, which used the flow direction grid to estimate accumulation in each cell of the output grid. And you can see how this works from the example here. In the grid cell on the middle right of this grid, 5 of the cells in the flow direction grid are contributing flow to that cell. Therefore, it's assigned a flow accumulation of 5. Obviously, the larger the grid, the higher the numbers you're going to get. And in the case of our grid, we used a cut-off flow accumulation of more than 100 to define a cell as part of a stream network. We derived a slope grid from the elevation grid to define flat areas, which we defined as having a slope of less than or equal to 0.5 degrees and being of greater than 10 metres squared in area. Sites that met none of these 3 criteria were excluded from phase 2 of the project, as they were considered not to have a topographical risk. We also used the digital terrain model to delineate catchments from the nearest pour point to the site grid reference. And a pour point is basically the lowest point to which water will flow. And this was the best way of finding the watershed or the catchment for the site grid reference. So phase 2 then was simple rainfall runoff modelling. We wanted to do this as a way of ranking the sites that had passed through phase 1 to identify those that were potentially high risk of pluvial flooding. We used an old ADAS method to do this, which, like I said, estimated peak flow for sites with a topographical risk. And this method is based on the popularly used modified rational method. You may have heard it described as the Wallingford procedure. But the difference being that it estimates peak flow from design storms using what's known as the Willem formula. So you can alter the intensity of your rainfall event. The parameters that the phase 2 tool required were the area of the catchment, the standardised annual average rainfall in the area, a soil index, which is essentially a standard percentage runoff for the catchment, which was calculated using National Soil Research Institute soil data, and also with an estimate of the percentage of the surface of the catchment that was impermeable, which was estimated using aerial photography for each catchment site. The other parameters were the length along the flow path and the average height of the catchment above the site, which were both estimated using GIS tools. So once we'd calculated a peak flow for a 75-year return period for each site, this was then used to rank those sites in increasing order of peak flow. And the idea was that the top ranking sites amongst those would be the ones that you would expect to need to prioritise for site visits. Moving on to phase 3 then, which was the site visits themselves. We surveyed 3 sites. 2 of those had been identified as high risk by the screening tool, and the other was known to have previously flooded due to pluvial flooding. So the site visits aim to assess the pluvial flood risk on the ground using established methodologies. Also to define the extent of the surface water network, that is the urban drainage systems, and also to ground truth the catchments that we defined from the digital terrain model. So the results of phase 3 then were we found that all 3 sites were close to the topographic features that we'd identified in phase 1. All were found to be at some risk of pluvial flooding due to one or more of the following factors. All of the sites were found to have poorly maintained drainage systems, which exacerbated the problem in all cases. Some also had blocked catch pits and ditches surrounding the site. One of the sites had poor drainage on the adjacent land, which was a flat area of field, and another had problems due to surface runoff from an adjacent road, which channeled the flow down towards the site. And the picture here is an example of a blocked drain actually on the road, which caused the water to overtop the curb and flow down into the site. So what we were finding here was that the remotely derived topographical features and also the catchment characteristics direct surface flow towards the sites, which are then turned into flood risk hazards by poorly maintained drains, etc. The ground truthing of the catchments resulted in alteration of the catchment boundaries of all three of the sites, and this was in part due to the location of the pour point in the original analysis, which I'll talk about in a moment. The catchment delineation was also influenced by the urban infrastructure surrounding the site and the microscale topography, which are things that can't be picked up from the remote sensing. Now, we found afterwards that using the entire site boundary for delineation of the catchment from the DTM gave better results, as I'll show you in this example. So on this example, the beige polygon at the centre is the extent of the site. The red dot is the pour point that was the closest pour point to the site coordinate that was found in the modelling phase. And the red line is the catchment that was originally defined from the DTM. The blue area, the blue line, is the catchment that was derived from the site visit. And as you can see, it incorporates an area of field to the west of the site, as well as quite a large proportion of the housing estate to the north. And the original catchment in particular didn't capture this area to the west of the site. The yellow arrows are the direction of surface water flow that was assessed at the site visit stage. Now, when we recarried out the catchment delineation using the beige area as the source of the catchment rather than the pour point, this resulted in the black catchment you can see on there, which more closely matches the blue, certainly in the area to the west of the site. And the reason that it didn't pick up all of the housing estate to the north was that the surface water flow contributing to the site from the housing development is due to the surface water drainage rather than the topography of the land. So the results of phase 4, which is the refinement of the methodology, show that the area of the catchment has a large influence on the estimate of our peak flow, and the catchment extent also has implications for the percentage of the impermeable surface that's estimated, and also the flow path length. But using the new methodology for delineating catchments, we found that these more closely matched those estimated at the site visit. So in conclusion from phase 1, I talked very briefly about the resolution of the digital terrain model. We used a 10-metre DTM, which provided very good value for the result at £33 per 100 kilometre square. And this is important because, like I said before, the extent of the assessment covers such a large area, and this DTM has full coverage across the country. Now, a lot of urban flood risk modelling uses LiDAR or IFSAR data, which is superior because it uses airborne laser scanners and captures data points at much smaller intervals. But it's very high cost, as you can see, compared to the 10-metre DTM. And that would be prohibitive for this kind of large-scale assessment. So overall, we found the performance of the topographic analysis to be reliable, but the use of the DTM to define the catchment is highly dependent on the location of the pour points. In conclusion from phase 2, which was the rainfall runoff modelling, we can't conclude anything too much about the accuracy of the ranking of the sites without further site visits, because just 3 visits isn't enough to do this. but we did find that one of the sites visited was at high risk from pluvial flooding, but it wasn't ranked highly using the tool. And this was mainly due to the inaccurate estimation of parameters due to the delineation of the catchment. From phase 3, which was the site visits, the conclusions were that the microscale topography and the surface water drainage maintenance were both important factors for flood risk. The differences in the catchments that we found from the DTM originally and the site visit were largely due to the inaccuracy of the pour point location. And there was also modification of the flow due to built structures and also surface water drainage networks. So the conclusions then from phase 4, which was modification of the method, were that we can improve the catchment boundary delineation by digitising each site extent to use as the source grid, rather than relying on automatic allocation of the pour point. And recalculating the peak flow based on these revised catchments resulted in a ranking that was in line with the evidence from the site survey in terms of which site was most at risk. So going back to the original question, can we estimate site level risk at a regional scale? I think we can conclude that for a fully accurate flood risk assessment, a site investigation is essential. This is because of the microscale topography and the man-made features, and also the state and maintenance of the drainage systems, which can't be picked up using remote assessment methods. However, as a cost-effective method for screening sites for prioritising visits to these sites, this approach is promising. Thank you.